going to introduce you the next speaker, which will be, and again, I hope to pronounce it correctly, Benjamin, yes? Okay, with the surname I will just say it. Pajot from AMD. And we also have Miguel Terol from Lenovo. And they will talk about how to target the right AMD solution when running weather and climate applications.
Where is the pointer?
Okay, hello everybody. So I know many of you know me, but for those who do not know me, my name is Miguel. I'm running the technical sales team at Lenovo. I'm one of the usual suspects of attendees here every year. So for many years in a row, Lenovo is sponsoring this event. So I would like to take just 1 minute of this time to appreciate and thank a lot the organization of Do It Now. So for now, I'm going to, this time I'm not going to entertain you with any of our commercial messaging, and I will leave the stage to one of our closest collaborators in technology, AMD. Benjamin Pajot is going to tell you a lot of interesting things for you bright minds that are interested in numerical weather models. So please, Benjamin, and thank you very much.
Okay. Hello, everybody. Thanks for offering me the possibility to speak with you today. I came today with my colleagues, Simon and Sandra, so if you would like to discuss later, do not hesitate to reach us. I've got the hard task to be the last speaker before the lunch, so I will try to be sharp on time, but anyway, you will have to suffer my French accent. Today I'm going to speak about the process that is leading to select one AMD solution or another when you are running weather and climate application. I wanted this presentation to be a little bit a kind of what's happening behind the scene. Because there is not one CPU or one GPU that is fitting all the scientific codes requirements. We've got regular exchanges with the vendors in order to discuss and find the best solution. For example, I've got a fortnightly call with Lenovo benchmarkers and architects. They are great experts. We've got a very fruitful discussion. But they need AMD insights in order to get the relevant technical information to distinguish our products. So one question that is leading our discussion is how to link the hardware features to the performance of the code. So in this presentation, I'm going to speak a lot about code characterization. Are they memory bounded, compute bounded? Is it a little bit more complicated? And I can disclose from now on that it's a little bit more complicated. Okay, all the centers are running weather and climate application. They are using different codes. Maybe you are familiar with names such as Elfric, VAR, IFS, Arrow Arpège, Icon. Even if they belong to the same field domain, I will say, they are implementing different physical discretization, minimization algorithm, numerical strategies. Talking about the physical discretization, for example, they can rely on finite difference methods, they can use spectral elements, they can move a part of the computation to the spectral domain using spherical harmonics, whatever. The consequence is that each code is behaving differently and leveraging more or less for the compute capacities from the memory bandwidth and so on. And this is what we need to assess. This is a preliminary work that we are helping Lenovo to do in order to reach their targets, that is, to make the customer being happy, because we like happy customers. So all the 6 centers are running with EPYC CPUs, and we are hoping that they are happy customers. Talking about the EPYC product, AMD has kept being innovating with this product. The first generation, has been launched in 2017. AMD made the bet of the chiplet architecture. I guess that it was a smart choice because we are seeing the competition adopting this kind of architectures. With the second generation, we have increased the core density. We have added an I/O die. With the third one, we have changed the way that the L3 cache is handled with 2 CCX per CCD. We have also some CPU with an extended L3 cache. With the fourth one, it was with a new socket platform. We have increased the number of memory channels, still the core density, implemented on the microarchitecture level, the double pump AVX512 vectorization. And today you can run with the 5th generation with a CPU made up to 192 cores. In the following, I will often refer to the 4th generation using the little codename Genoa, and about the 5th one using the name Turin. But talking about Turin, there is not only one Turin. If all the Turin have got the same feature set in terms of the number of memory channels, of memory speed and capacity, security, I/O, thus providing your customers a consistent feature set. The whole stack is meeting a wide diversity setup of use case. So a Turin can be made up from 8 cores to 122 cores, so that's a big jump. It can run with a different core clock, consume different amounts of power, be equipped with different quantities of L3 cache. So when you are running your code, what is interesting you? Are you going to target the highest core density, the one with the high frequency, with cores that can run up to 5 GHz, the one that is equipped with the highest L3 cache, or maybe you are interested in the performance per watt? Okay, that's what I'm going to speak about in the following. But before that, I just want to do a reminder regarding the EPYC architecture. Here it is a figure showing the architectures of a 96-core Turin. His little name is 9655. And you see that in each corner, you've got 3 CCDs, 3 core complex dies. And all of these dies is equipped with 8 Zen 5 cores, sharing a common L3 cache of 32 megabytes. What is interesting is to see that if you look at the upper left corner, the 3 CCDs will have a more direct access to the 3 UMC, that is the Unified Memory Controllers, and behind this UMC, you've got the DIMMs. So that is telling you that when coding, you should take care to the memory allocation, for example, leveraging from the first touch policy. Also interesting is to look at the links between the CCD and the blue box. These links are called the GMI links, the Global Memory Interfaces links. And what it is telling you is that if you are using 4 cores on each CCD or all the cores, that does not matter. You will be able to retrieve the maximum memory bandwidth available till the fact that you are using each of these GMI links. Alternatively, if you are only using one of the 3 CCDs over this NUMA node, it will have an impact on your performance. And I am illustrating that in this, with these 2 figures. So what we are looking at here is that at the memory bandwidth measured on one NUMA node using the STRIM benchmark. STRIM, it's a well-known synthetic code, kind of gold standard. And on the left, I am plotting the measured memory bandwidth for Genoa using 1, 2, or 3 CCDs. And on the right, it was for a Turin that is equipped with 4 CCDs per NUMA node. So plotting is the memory bandwidth for 1, 2, 3, or 4 CCDs. And we see that it's necessary to use at least 3 CCDs per NUMA node in order to retrieve all the memory bandwidth available. it's interesting to consider, first of all, when we are doing characterization, but also if, for example, you are running an NPMD, and you know that there is a load imbalance among the processes, so likely you will increase your performance if you are spreading your processes over the CCDs rather than grouping them into one CCD. Okay, now here we are. What are the hardware metrics that are driving the performance? Of course, the number of cores, but going further, what is the delivered IPC, the delivered instruction per cycle? What is the part of this IPC that are coming from the vectorization, the FMA, the instruction pipeline that you've got, and also what are the data types that you are considering and how that does impact your IPC? Talking about the memory bandwidth, this one is depending on the number of memory channels, the number of DIMMs that are keeping the memory channels, because it can change the memory speed, so your memory speed also, your bus width, and the efficiency of your DIMMs. Are you running with a single rank memory or dual rank? It has an impact. And likely your code will do some I/O, and it will communicate over the network. Okay. In the following, I wanted to illustrate that there is not one characterization for one code. So in this first story, I'm showing that I'm using one code, but with two datasets. Here is the work that I did a few years ago. We were working with a customer who wanted to. He was using the code, the Unified model, the code UM, and he wanted us to know how his code was behaving. So he shared with us a first test case, the TC1. That was a very small test case. So I began doing my stuff. I exchanged with him the first results, and I said to him that it would be better to share a test case more representative of a production test case. The first tool that we like is a roofline. With the AMD MuProf tool, I can easily generate a roofline. Just briefly, to remind, a roofline is computing when you are running an arithmetic intensity, so that is a number of operations of flop that you are doing with each byte, and also a throughput, a number of operations per second. So it is plotting here, in this case, this little red circle, and it is adding to this figure your this slope here that is representing the roof of your hardware dependent on the memory bandwidth available, and the horizontal roof is the roof made by your compute capacities. What it is telling you is that if you are near the roof, likely you should think to a new numerical strategy in order to move your point and change the arithmetic intensity of your code. But if you are far from it, there are many interpretations. Likely here I am running with a small test case, so I am not benefiting from all my memory bandwidth. But there are also other parameters that can have an impact. But what it is not telling you is that if you are behind the memory roof, that your code is not dependent about the CPU frequency. I've got the ability to decrease the CPU frequency of my cores. So the yellow little circle is throughput measured when I am setting my frequency to 1.5 GHz. And you see that when I am increasing this frequency towards 3 GHz, I am improving the throughput. So that means that likely a part of my runtime is dependent on the CPU frequency. Also here, I still have the same figure on the left as the previous one, and on the right, I have changed simply the I/O file system that I was using, and you see that I have improved my throughput. So roofline is a great tool, but it's not necessarily sufficient when doing characterization. Talking about I/O, you know that AMD is not a storage provider. So what we like to do is to assess the I/O part in our runtime and to try to come with I/O parts. For that, we can use libraries such as Darshan, for example. In this example, it was happy for me because I had several file systems that I can use and that allows me to let this I/O parts become negligible. For example, on the left figures, the dark purple elapsed time, is the one dedicated to the I/O, and when I am running on my local disk, it is becoming negligible. For my bigger test case, this is a dark green part, and when running on BGFS, this I/O time becomes negligible. So I am happy because I will be able, in my characterization, to remove that part. Okay, here it is kind of yeah, there are lots of data on this figure, so I'm going to explain you what we are looking, what it is telling us. First thing that sometimes we do is to play at we have the ability to change some BIOS parameter and to change at the system level the number of NUMA nodes per socket. So looking at the TC1 results, here I am running, considering 1 NUMA node per socket, 2 NUMA nodes per socket, and 4 NUMA nodes per socket. It's not very visible. There is a little bit of improvement when running with 4 NUMA nodes per socket, but overall the patterns remain the same. Also, we are disabling a certain amount of cores per CCD in order to look at the intranode scalability, and I am seeing that with this test case, running with 1 core per CCD till and increasing the number of cores till 8 cores per CCD, I am improving a little bit the runtime. I am running with boost disable, that is the dark blue results, and with boost enable, and the boost is giving some performance. And the last parameter that we are playing with in this figure is to enable or disable the simultaneous threads, so the ability to use logical cores. And we see that with this this small test case, it has really not impact on the performance. But when I am looking at my bigger test case, the pattern is totally different. When I am using a low number of cores, it is improving the performance. This red part, you should subtract them from the whole column in order to get your runtime performance when using them. But when I am running with all my cores, it's not anymore, in this case, giving an extra performance. Likely, there is an issue with a bottleneck at the level of the L3 cache. So one interesting thing could be here I was running with Genoa to look at what will be the results if I am using a Genoa X with an extended L3 cache. Here, this is somehow the most common experiment that we are doing. We are playing with the memory speed and with the CPU frequency. So looking, for example, on the figure on the right, I am running at 1.5 GHz, at 2 GHz, 2.4, 2.8, and I am plotting here the relative performance compared to the performance that I am measuring at the slowest CPU frequency. And what we see is that with my bigger test case, the TC2, my performance is much less dependent on the CPU frequency than it is the case with the TC1. And that is expected because we are more relying on the data transfer and so on. And when I am looking on the figure on the left, this time I am playing with the memory speed, running at 3200 megatransfer per second to 4800 megatransfer per second. We see that I've got the opposite pattern. So, pre-conclusion is that I was running the same code, but with 2 different data sets, and I am ending up, we saw that, with different characterization. This is a last slide on this test case. Also, we are looking at the memory usage. Here I'm using MuProf, and it is showing me on the figure on the left, for example, the read bandwidth per memory channel in function of the time. So one good point is that it is a balance over my memory channel, but we see that with this small test case, there are lots of time of where there is no data transfer, and you are seeing a lot of yellow. Okay, next story. This time, same code, same test case, but different architectures. So for this story, I am using the Integrated Forecasting System, IFS. I am running a big test case, and I am running it on a 12 node. Each node is equipped with two CPU, two 192 cores Turin. There are two metrics that I would like to highlight there. That is first the theoretical memory bandwidth per core, that is with the CPU of 3.2 gigabytes per second, and the L3 cache that is of 2 megabytes per second. In fact, there is also a third metric that can matter, that is the amount of power available per core, but this one will have an impact on the CPU frequency, the sustained CPU frequency. So somehow I can choose to run at the nominal frequency, or I can monitor that during my run. And I am also using another CPU. I am simulating it. In fact, I am using 1 core over 2. And this way, I am doubling the theoretical memory bandwidth available per core and the L3 cache per core. The way the L3 cache is made is with our CPU is that it is made of 4 stacks. And we've got the ability at the operating system level, using the MSR register, to say to the system, you will use all the 4 stacks, 3 of them, 2, 1, or not at all the L3 cache. And so this way, I can look at what is the impact of decreasing the amount of L3 cache available. And what I am seeing there is that when I am dividing this amount of L3 cache per CCD from 32 megabytes to 16 megabytes, the relative performance is 14% slower. So I am happy because I can extract this part of my characterization. Now, looking back to the same figures as previously, so I have presented them. This time, the red line is when I am using the full node, so all my 1T2 cores. And we see that, for example, doubling the CPU frequency from 1.5 GHz to 3 GHz, I am only improving the performance by 30%. Whereas when I am using all my cores, I am benefiting from a higher memory bandwidth available per core, and I am increasing this performance from nearly 80%. Looking at the impact of the memory speed, as previously, we see that the opposite pattern this time the full node run is more dependent on the memory speed, and using half the core is less dependent. So to conclude with this first part of my talk, when you've got one scientific code, you don't have one characterization. This characterization will depend on your dataset, on your hardware. And somehow this is why the work of the vendors is not so easy. Okay, now a few slides regarding the work that we are doing with GPU. I would like to thank my colleague Paul Mulony, because he really is the brain behind the results that I am going to show. The ECMWF is developing a code that is moving a part of the weather forecasting computation using the outputs from machine learning. This code is called Artificial Intelligence Forecasting System, AIFS. It's not only a research project, but it's already in production since nearly 1 year now, and we are collaborating with them since a few years already. And here I'm going to show you a few results running this code for inference and training with our latest GPU, the MI325X and the MI355. Here, it is a profiling, a timeline of the activities when doing an inference. So you see that 80 to 85% of the time is spent on the GPU. So we can be rather happy with that. Most of the computation are done on the GPU, but it remains that 15 to 12% of the time is spent on the CPU. So maybe it should be interesting to think to strategy in order. Just 1 minute? Okay, to recover that time. Yeah, so we've played with the scalability of the inference on one node. Okay, pretty good scalability, not perfect, but you should prefer to run 8 inference. That's my point of view. We've got a nice uplift, and we also happy to see, we have proposed to our customer to implement another subscription strategies. That is because we've got MI355X with a high amount of HPM, we are able to run 2 inference at the same time on the same GPU for just a 5% increased runtime. I had some results regarding the training with the uplift from one GPU generation to the next one, with a weak scaling test, going from running on 1 node or on 4 node, increasing the ensemble size. And because it is the end, pay attention to this one. It is very important.
My question is IFS ready to be ported to GPU with some GPU offloading or something like that? Given the commitment of AMD to provide high performance for FP64 and FP32 floating point data types. So is there any way that IFS, not AIFS, but IFS, to leverage GPU performance?
Yes, there is a way. It's a work in progress. So I think that's in the plans of the ECMWF to move the production to the GPUs one day, probably. But all these weather applications are somehow very complicated to port to GPU because they've got flat profiles, they have a high level of requirements for validation, and these codes are millions of lines of code. So it's a complicated work, but they are working on that.
Thank you.
Coming from a weather company, so my question was in line more or less that yes, they are porting part of IFS to GPUs, but if you have experimented with other models like Icon, the ones that have already GPU versions with your hardware?
Personally not, but my colleague Paul Mulony has got. So if you want to exchange about that, I can arrange a meeting with him.
Yeah, thank you.
Any other question?
So thank you very much for the talk. So you mentioned that numerical methods have a big influence, of course, on all of this optimization outcome. What about the programming language? So if they use Fortran or C++, what is the effect of that?
I don't know if I am the most skilled person to answer that question. I will just speak regarding what I am observing. I think that considering Fortran or C++ won't be somehow an issue. What we see often with C++ is that people tend to implement very nice features, and but that are not well optimized, and that at the end they are doing exactly what they want. What we are putting that in a whole framework, it's more complicated to optimize that perfectly. But yeah, till the time that you are not using Python, I think that even if that it's already progressing from that point of view for this language.
There is actually, is it working? So there is actually a competition across all the programming languages, and there's a bunch of benchmarks available there. And there's a website that is actually gathering all this information, programming common algorithms to reveal the performance achieved for every single programming language. If you explore Chapel, which was all processed from Cray, so on the website you can see the mapping, and you can see the comparative analysis on the performance for all those applications and all those benchmarks.
Okay, also for like weather prediction?
No, not in the weather, it's
Okay.
on the programming language.
Yep.
So comparing, for example, Lulesh kind of a setup, comparing the same algorithm on Python with Fortran, C, C++, and things like this. So then you can see the speed up that you can achieve. That's okay.
Any other question? Okay, so thank you very much, Benjamin, and thank you to all the speakers for this morning.